So my title is Design for Good or Evil, which is your theme for this year. But I'm talking specifically about system utility and conceptual fit, how we design systems that are actually fit for purpose. So let's start by thinking about what makes a good system. You probably all have your views about this. But I suggest that it's a system that is easy to learn, easy to use as intended, efficient, effective, satisfying, engaging, safe, bringing pleasure, bringing positive values into the world, supporting collaborations between people. And you can probably think of many other criteria as well. What's perhaps important is that much of this isn't surprising, it isn't remarkable. We don't really notice a lot of the time when a system is good, when it works well. Just as a quick aside, what makes an evil system? Well, arguably, it's a system that supports evil activities like terrorism or pornography. Of course, the same systems that support evil activities often can also be used for good as well. So that's a difficult theme to kind of pursue in any depth. So more commonly, it's less extreme than that. It's systems that cause frustration, that force people to be inefficient because the interaction isn't smooth, that provoke errors, that facilitate privacy violations, that make it easy for people to accidentally share information, for example. They're systems that make people disempowered and feel vulnerable. So I would say that these are systems that don't really fit their users. And we're going to focus on that as a theme for today. There are a lot of methods that have been developed for designing and evaluating systems from a user perspective. The little diagram I have on the right here shows the standard International Standards Organization representation of a classic usability, user-centered development lifecycle. So we start by identifying a need for user-centered design. We understand and specify the context of use. We specify the user and organizational requirements, implement design solutions, evaluate those solutions, realize they're not quite right, kind of understand the system better, go around that iterative cycle several times probably, and end up with a system that satisfies requirements. And along the way, we use a lot of different tools. We might use personas and scenarios, design patterns, task structures, ways of representing the conceptual design, information architectures, storyboards, methods for participatory design and co-design. You can probably think of many others, and you've probably learned or are practicing many other similar kinds of techniques. So I'm going to focus in this talk on mental models and conceptual models, particularly the latter. These are ways of reasoning about the gulfs between people and systems. Most user-centered approaches, such as the ones I just described, tend to focus on features like usability, learnability, satisfaction, task structures, the procedures that people follow when they complete tasks. And you'll find that most of the established techniques don't pay very much attention to conceptual fit, which is what I'm going to focus on today. And conceptual fit is really about the question, are we building the right system? Does it really fit with the intended users? So a little bit about conceptual models and mental models. You may well have heard of mental models before. There are lots and lots of definitions of a mental model, probably as many definitions as there are people who write about the subject. Broadly, it's how people understand the thing that they're working with. My favourite definition, which is actually a very old one from Dave Keiras, is the how it works knowledge together with the how to use the how it works knowledge, i.e., you know how something works, or you have an understanding of how something works, and you also are able to use that knowledge to be able to interact with that thing. Dave, in his description, focused largely on physical interactive devices like clocks, like electronic and electrical equipment, but the same applies to all sorts of other domains. For technology use, apps, websites, mobile, wearable technologies, the users have mental models of how that technology works and how to use it, how to interpret data from it, how to fix it if it goes wrong. And we get stuck when our mental models aren't adequate for the purpose. I work quite a lot in healthcare, and some of my examples in this talk are going to be taken from healthcare. And we find that clinicians have mental models of how our bodies work, of how we work, what makes us tick, and importantly, how to fix our bodies, using the tools that are available to them when it goes wrong. So giving us medications, giving us different kinds of therapies, telling us to go for long walks or to avoid particular foods, etc. So, mental models feature in a lot of different contexts. An early example, which is actually taken from a book by Chip and Dan Heath called Made to Stick, which is really about the power of storytelling. One of the stories that they tell in that book is about a baby in neonatal intensive care. So already a very sick child, but this baby suddenly turned a kind of blue-black colour. However, the heart rate monitor indicated a normal heartbeat. So the team, working on the available evidence, assumed that it was a collapsed lung and prepared to treat that, which is quite an invasive treatment. However, one of the nurses in the team wasn't convinced that that was the right diagnosis and suspected pneumopericardium, which is a condition where fluid gets into the chamber around the heart and compresses it so that the heart can't beat properly. So that nurse listened with a stethoscope and indeed could not hear a heartbeat and realised that that was the correct diagnosis and hence could administer the effective treatment in that case. So what do we have here? We have a case where the heart rate monitor was indicating that electrical signals were being sent to the heart to create the heartbeat, which was interpreted as being a heartbeat, but this was not actually an effective surrogate in this particular case for actual heartbeats. The technology was not lying, but was open to misinterpretation in this context. So Smith and Koppel, in a paper back in 2014, kind of talk about mental models relating to clinical care, such as the care of that little baby. They talk about traditional mental models for clinicians. We have the real world, how things really are. In this particular instance, a small premature baby has a condition that means that they've got fluid around the heart and is not able to beat properly. And then we've got clinicians' mental models of how things work, how clinicians understand what's going on in our bodies, which in that case was actually open to multiple interpretations initially. But we also have now technology-mediated understanding of the situation in the real world. So we have the real world, how things really are. We have reality as represented through the technology. So in this particular example, the technology, the ECG monitor, is showing that the electrical impulses are going, which implies that the heart is functioning normally. And that, together with the evidence of the baby, direct observational evidence of the baby having turned blue-black, contributes to the clinician's understanding of how things work for this particular baby and more generally. And it took the use of a lower technology, i.e. a classical stethoscope, to help the clinicians to refine their mental model of what was going on in this particular situation. Smith and Koppel talk about 5 different kinds of mismatches between the reality and the mental models as mediated by technology. The first is that the information is too coarse, that the technology doesn't communicate all the necessary information. And we might say that the example of the ECG monitor was doing that. It was missing details that matter about whether or not the heart was actually beating, because of course that's not what an ECG monitor is designed to do. The information might be too fine, demanding details that don't matter or that aren't known. So you're asked to enter some number into a spreadsheet that you don't, or into a form that you don't know and that isn't going to make any difference at the end of the day, for example. It may be missing elements of reality that matter. Actually, the example of pneumopericardium perhaps fits that class better. It wasn't that the information was too coarse, it was that the information was incomplete. So forgive me there. It may be representing multiple realities, there may be multiple interpretations from the data, or the information may be incorrect. For example, it may come from sensors which aren't accurate. You might have, think of your Alexa or similar kind of, sorry, I've forgotten the word, similar kind of system for hearing and interpreting voice. We don't have an Alexa at home, but our children do, and often it doesn't understand them or it misinterprets them. It's not very good at getting the information correct. So Smith and Koppel give 45 examples of different kinds of mismatches in their paper. It's not an exciting read, but across that set of examples, there are some very valuable insights. We'll come back to Smith and Koppel a little later, but for now, we'll think about mental models and conceptual models. So mental models are typically informal. They may be picked up through experience. They may be picked up through education. You may be trained how to use a particular kind of technology. Clinicians are trained on how the body works. Conceptual models are more formal and are used for reasoning about design. They have a structure that designers and users work with to enable us to think about design in a more precise kind of way. Don Norman talks about conceptual models in terms of a match or a mismatch between the designer's conceptual model and the user's conceptual model. And the designer creates a system representation, a computer program or whatever, that the user needs to work with. And the user brings a conceptual model, their own conceptual model of how that works, to work with that system representation. And the thing that most strongly informs the user's conceptual model is the system image, the way that the system projects itself, the things that appear on the screen, the haptic messages, the buzzing and vibrations of a phone, or the sounds, or different forms of system image that help the user to form and refine their conceptual model of what's going on in this context. But we have historically talked about these things in a fairly kind of hand-wavy way. And in our work, we've tried to formalize that, make it a little bit more systematic and rigorous. So we developed this method called CASSM, which stands for Concept-Based Analysis of Surface and Structural Misfits. Don't worry too much about what the acronym stands for, but the word is intentionally kind of sounds a bit like gulfs between users and systems. So CASSM is about identifying those gulfs between the user model and the device conceptual model. And it's a kind of structured approach to doing what Smith and Koppel did, and also what Norman describes in his approach. So the idea behind CASSM is that the system should be obvious. It should be understandable to users. It should be helpful. It should work with the way that people think. I'm going to start with a really simple example. A tap, particularly a tap that's designed to deliver water at the temperature that you need it to be. Of course, the system model, because in most countries, the hot supply and the cold supply are delivered to the tap separately. The system model, as exemplified in my bath tap here, is that you've got hot water pressure and cold water pressure. And to change the pressures, you turn the corresponding tap. In this case, we've got the hot tap labelled red on the left and the cold tap labelled blue on the right. And when you turn them, you change the you manipulate the temperature, but you also manipulate the pressure of the water that comes out of the tap or out of the shower head. Of course, what we want as a user model is that we care that the water comes out at the right temperature, and particularly if it's a shower, that it comes out at a comfortable pressure. Not too fast such that it hurts, not too slow that it doesn't get the soap off. And we need to be able to map between these views. And this tap in my house is quite old. We just haven't changed it. We haven't changed that particular bit of plumbing for a while. But we have 2 bathrooms, and in the other one, we have the other kind of tap that actually matches the user model much better. So on the left, where you can probably read the word stop, it can be turned one way to control the pressure of the water to the bath, and the other way you turn it, and it controls the pressure of the water going to the shower head. And then on the right, where it shows 40 at the moment, that just controls the temperature. That doesn't control how the water comes out. It just controls the temperature at which the water comes out. So this tap represents a much better, much closer representation to the way that we think and the way that we want to control our taps. Taps is not a very exciting example, but it's a simple and pervasive example, which is why I've used it here. And if I'd physically been with you, I'd probably have started to tell you stories about the tap in the hotel where I'm staying, but unfortunately that's not possible. So CASSM relates the user's perception of the domain and the device. We've learned to use the other kind of tap, the old one with the red and the blue controls. So we can understand it and manipulate it. It's just not so easy. So we're relating our perceptions of the domain and of the device that's being used to the system and the interface implementation. Focuses on concept, the things and their attributes. In this case, the flow of water and the attributes, the pressure and the temperature, rather than the procedures. If you imagine writing a procedure for getting the right temperature from your shower, it's not something we would naturally do. Sometimes I use the algorithm of the procedure of turning the hot tap to maximum and then turning the cold tap to maximum, and it often comes out cold then. So you gradually turn the cold tap down and wait a bit, tap, still too cold, turn it down a bit more, wait a bit. Is the temperature right yet? So it's a long procedure to actually get the temperature right if you've got the 2 different kinds of taps. Whereas, of course, with the more recently designed tap, that procedure is much simpler to describe. So we don't tend to work in terms of the procedures, we tend to work in terms of the concept. Or for this particular method, we think about the concepts first. We identify misfits. And for CASSM, the focus is on redesign, assuming that you already have some form of technology to inform the redesign. This is not so much used for design kind of from first principles. But then very few technologies are actually designed from first principles. Most are an evolution or a development of something that already exists. So the core concepts of CASSM are entities, the things that people are working with that can be perhaps created or deleted, or that have attributes. And attributes are then properties of the entities, which can commonly be changed. If nothing can be changed, there's no point in talking about it, really. And then actions are the things that people need to do to change the state of an entity or an attribute. And I hope this will all become a lot clearer as we go through some more examples. So how do we define concepts? Or how do we identify concepts, rather? Well, the answer has to be data. This is an empirically driven approach. From the user side, verbal data from people is the best way to identify the concepts that people are really working with. We might gather that through interviews with people, through think aloud of them using a technology. That's a slightly more device-oriented way of gathering data. Interviews asking what people are doing in the world is very often the most effective. Approaches in the workplace like contextual inquiry, where you observe what people are doing and then ask them about their work, their activities. That could get at a lot of the key concepts. Focus groups, which are kind of like group interviews. Or occasionally, if you don't have access to real users, you may rely on rich descriptions of what people do and a certain amount of expertise. And then system descriptions or interface descriptions may come from working with a running system, may come from a system description like a specification or a storyboard or prototypes. Many, many different kind of sources of data that you might work with. In terms of a user perspective, we have our user trying to do something in the world, as represented here, via a computer interface of some kind. Of course, this is a big old-fashioned monitor. Many interfaces are much smaller, much sleeker than that now. But big old-fashioned monitor helps me to do the slightly crazy animations I'm about to do. So in some way, the world is represented through the interface. It's rarely represented perfectly, so to be a slightly imperfect view of the world that you see that way. Things will be missing, things will be at too high a level of abstraction, too much detail, etc. Underneath that system, there will be things in the internals of the computer system that sort of don't matter. They're the things that make the computer system work. You know, there's a system clock, there's ways of moving bits around within the software. We don't really care about those. You know, if we worried about those all the time, we'd never get any work done. But there's also tools that we need to use. I've represented these as very physical tools here, but they are, you know, the things that we use at the interface, the widgets, the keyboard, the things that we manipulate with the mouse, etc. And those are the things that the user has to understand. They need to understand the world, the representation of the real world, and how to use the widgets to change the real world. So when thinking about the device, how you describe the device or the system, you should focus on domain relevant concepts, not the detailed design of every interface widget. You wouldn't be too worried about how the hammer is constructed. You'd be worried about what you can do with a hammer in order to change your device. That's probably a bad analogy. So people have to interact with widgets to manipulate domain concepts. In my example here of a slightly weird and rather primitive person, one thing that people do have to understand if they're going to create drawings of this kind, preferably better than mine, are what I'm calling the handles on the face, the little rectangles that allow you to manipulate the size and the shape of the face, or indeed to change its colour. So you might include those in the analysis, but the detailed description of all the tools in the tool palette is too much detail probably and a waste of time. In a lot of situations, the interface and the underlying system representations are very, very similar, so you just kind of merge them together. Sometimes people can infer things from the interface that aren't really there in the underlying system. So hopefully above, if it's not masked by my image, you're able to see a person. Of course, that person doesn't actually exist as a system representation. The system representation is some circles and rectangles and little heart shape. Less commonly, there are important features in the underlying system that are not represented at the interface. So in many drawing programs where things are layered one upon another, it's very hard to work out the ordering of those layers. As I was preparing this talk, I thought about how are things layered in PowerPoint. And actually there is a way that you can access the layers. For this particular page, they look like this. You can see a layer at the back that has the title, and then a second layer that has the body text, and then the third layer has the little person. And I confess, I don't even know what's on the fourth layer there. I'd have to manipulate them to even work out what it's doing. But for simplicity, we usually consider the interface and the system together, except where that hides important features of the device that matter for thinking about how usable it is and how to make it easier for people to work with. Then the third thing, actions. Actions are linked with the entities and the attributes. So entities can be created or deleted. Often, maybe that's not possible. Attributes can be changed. And when we think about actions, they may be easy to do. It may be very obvious how to achieve a particular change in the system. It may be much harder to work it out. It may be moded. You can only do it when the system's in certain states, or it may be disguised. The labels may be unclear, or they may be hidden somewhere. It may be indirect. You can't do it directly at the interface. You need to find some way to work around to achieve the effect. It may be impossible. That could be a problem. Maybe it's fixed. Can't be changed, but that's okay. Or maybe it's done by something in the system or by another agent. But I'm now getting perhaps into too much detail. I'm just trying to give you a flavour of how this works. The key thing about a CASSM analysis is that you do as much as is needed to get at the key ideas, the key principles about what works well and what doesn't with the system. So you start by identifying the core concepts on both the user side and the system side. And then you gradually refine the description, pulling out more detailed concepts, thinking about whether they're present for the user, difficult for the user, absent, similarly for the system, whether they're entities or attributes, how easy it is to work with those things. But don't do more than is absolutely necessary. And then finally, there are notes. If you've done many analyses of interactive systems or thinking about design, you'll realize that the activity of actually doing that thinking, constructing a model, is the most insightful. And often that provides more insights than just looking at the resulting model that you get at the end. So it's good to keep notes as you're doing any usability analysis so that you capture all those insights as you're going along. And the whole point of doing an analysis of this kind, of course, is to help to improve the design. It's kind of a formative technique, not a summative approach. So I'm going to close with a couple of examples. This is based on some work we did a few years ago, and this is a picture of an ambulance in London. I'm sure your ambulances look a bit different from this, but they're probably not green and yellow, but functionally they do the same thing, and I'm guessing you have control centres that do very similar functions to the ones in London. So in the control centre, rather than on the vehicle, there are people called allocators. Allocators deal with incidents in the sense that they take information from incoming calls into the control centre and they decide what vehicles to send, how many vehicles to send, whether it's a classic ambulance like the one I've got in the picture here, whether it's a motorcycle first responder ambulance, Even in London, we have push bikes that can get to places faster than any other vehicles. Not very many of them, but we do have them. And of course, helicopter kinds of ambulances. So they have to decide what kind of vehicle to send, with what kind of crew, and how many vehicles to any given incident. The computer system that they were working with at the time that we did this study only allowed them to process calls. So every time somebody dials, in the UK it's 999, I realise many other countries it's 112 or 911 or whatever that emergency number is. You know, somebody has phoned up to report an incident that requires urgent medical intervention. And the computer system they're working with permits the processing of each of these calls. But actually, if it happens on the streets, very often multiple people will phone up about the same incident. So there'll actually be multiple calls that refer to and provide information about one incident. So at the time that we did this study, which it was a few years ago, but not that long ago, they actually worked with a paper system whereby they printed out a sheet relating to each call, and then they would look at calls that were in the same place, describing the same kinds of symptoms at the same kind of time, and decide whether they referred to the same incident or not. And they would then group those bits of paper together to reason about it as one incident rather than as responding to every single call. And so what we identified is a misfit between two concepts that were both referred to as called within the control room. So one was an actual telephone call with the information that it contains, and the other is the incident, the real world thing that has happened out there that is described through one or more calls. So, you know, in this case, we could say what the controllers need is a system that allows them to group information from multiple calls, sometimes to represent information about one actual incident and what ambulances have been sent to that incident, how many casualties there are to be dealt with, etc. So, you know, this is one example where two things the same word is used for two different things. There's a domain concept, what's actually happened in the real world, and a device concept, somebody phoning up, and the call record, that are similar but not actually identical. And the user, the allocator in the control room, has to map between those two kinds of entities. My last example, slightly distasteful perhaps, but really important in the medical world, is taken from the paper that I've already talked about by Smith and Koppel. And I mentioned that they had 45 examples, and I've literally just picked the first two from their paper. So the first one is about vomiting, where in a hospital, a clinician administers a pill to a patient, but then the patient is sick. And the question that Smith and Koppel ask is, has the medication been administered or not? This matters because, of course, the clinician is actually trying to get a particular dosage of the drug into the patient in order to have the right effects. And according to the system that Smith and Koppel were analysing, the medication administration record, the computer system, demands a yes or no answer. This idea that yes, it's been given, but no, it hasn't actually been absorbed by the patient, doesn't fit properly in the medication administration record. But of course it clinically matters, because the clinician then has to decide how to deal with that situation. Their second example they call Schrodinger's pharmacy, i.e. does something exist or doesn't it? A doctor has ordered some medication, so this is earlier in the process, before it's been administered, when it's ordered. But there's a phase of it being approved by the pharmacy. And they ask, does the order exist yet or not? So the doctor has issued an order, but it hasn't yet appeared as ordered in the medication record because it only appears there when the pharmacy approves it. And apparently this occasionally results in double dosing because if the pharmacy is running a bit slow, one clinician orders a medication for a patient, another clinician comes along, but it hasn't been recorded as such yet. Another clinician appears at the same bedside, recognizes that the patient needs it, checks, it apparently hasn't been ordered yet, so they order it as well. So 2 orders are queued up within pharmacy, and then 2 orders get dealt with and administered to the patient. So we get double dosing. This is not good design. It is not safe design. So presenting that example in the terms of CASSM, we see that on the system side, the only thing it really is concerned with is the medication, whether it's ordered or not ordered, whether it's been given or not given. Whereas on the user side, we have the medication ordered, not ordered, dispensed or not dispensed. So capturing that phase in the pharmacy where the pharmacist actually has to approve the medication order. And then it's either been given or it's not been given. So that kind of captures the second of those examples, the Schrodinger's pharmacy example. But there's also the important first example, which is about the patient who is apparently not represented adequately within the system because there's this important feature of have they received or not received the medication, i.e. not just has it been given or not given, but have they actually received it? Has it stayed down? Have they absorbed the drugs through that process? So I've gone into more detail in the presentation of the method than I have in the examples, because going into examples in that much detail is out of scope and we don't have time for that this morning, but of course you're very welcome to go and read the papers and indeed to ask me about anything you like about that method. So I've tried to focus a bit on designing for good or evil and given examples that I hope are motivating and compelling and show the importance of good design. It's not my own phrase, but I have heard HCI being described as the conscience of computer science, where the people who think about, is this good for people? Is this good for users? How do we make systems that work well for people? Our role is to optimize how systems work for people. That doesn't mean necessarily making the algorithms as efficient as possible, though that can help. It's making systems really fit to work with and for people so that people can do their best work, can achieve their potential. And evaluating and designing in terms of these kinds of user concepts that I've been talking about today is one important aspect of good design. It's not all of good design, but it's an important aspect that has often been overlooked. I am here, or not here, courtesy of the ACM Distinguished Speakers Programme, and I would particularly like to thank Johannes and Freddie for inviting me and for planning everything with me, and particularly for dealing with the fact that at the last minute I decided I really couldn't leave my father. The ACM, you can probably read this faster than I can read it out to you, but it's a global organization to help computing professionals to be their best and to be their most creative, to deliver on the latest developments, to inspire, advance the profession and have a positive impact on society. Seeing the values of computers where we use our knowledge and skills to advance the profession and make a positive social impact throughout the world. Those values are values for World Usability Day, and I'm sure they're values that you all share and that you will work with. I'd like to thank you for your attention. Hopefully I will be able to be online with you to discuss this, and are there any other ideas you want to talk about? But I've recorded it just in case the technology doesn't work. This is the backup. And I'll just close with the references that I've used for this paper, for this presentation, and wish you all the best for World Usability Day and for the week. Thank you so much.